So last time we talked about these kind of situations where you've got, a particular system. Let's see. Nope, don't want to do that. So we've got our system here, and we represent the internal energy of our system with a U, and then we've got U is equal to, what's our formula here that we talked about last week?
U is equal to Q minus W.
Q minus W. And what is Q?
Heat.
Yeah, heat absorbed. And so if Q is negative, then what you're looking at is you're looking at heat lost. And work tends to be negative. That is because typically your system is doing work on the surroundings, but it is possible for work to be positive if work is actually being done on the system and not by the system on the surroundings. And so this gave us a nice way of thinking through, okay, well, what does heat mean in terms of internal energy? What does it mean in terms of internal energy if you're talking about your system needing to do work? But ultimately, it leaves you asking a lot of questions like, okay, well, how do we actually relate heat absorbed to something that's actually measurable, right? Because when you're talking about the amount of joules of heat absorbed, that's not a straightforward, really easy concept to understand what's actually going on. So this week we'll talk more about that. So we're gonna kind of focus in on the Q, and so we've got this equation here. Q is equal to MC delta T. And so this is where we've got some important concepts. First of all, we've got our M, we've got our C, and we've got our delta T. Delta T is probably the most straightforward. This is change in temperature. And then the M is actually fairly straightforward as well. This is mass. Let's do it further up here. And then the C is what's specific heat. So this, for the C, you tend to need to know what your specific heat values are so that you can plug them into any particular solution. Now, most often when we're dealing with these kinds of problems, we're dealing with water being the fluid because, for several reasons. One, water is what's called the universal solvent. Do you know the term solute and solvent? So we've got a term that's called solution. And what a solution is composed of is, I don't want to do that, is solutes plus the solvent. And these solutes are what's dissolved in the solution. The solvent is the fluid component. Well, usually fluid. It is possible to have a solution where your solvent is solid, but that's unusual and it forms like a gel. A gel would be probably the only real example of where you can have a solution and have your solvent be a solid. But you could argue that it's more like a semi-solid than an actual solid. And so water is what's called the universal solvent. And what that means is that basically water forms the solvent in almost every aspect of life. Inside of cells, outside of cells, inside of like extracellular matrix, that water is the main solvent. And so that's why we tend to work these problems with water, is because water is the universal solvent. Also, the reason we tend to use water is water has the highest specific heat of any substance on Earth. Okay? At least as far as I'm aware of. And water specific heat, or C, is equal to 4.184 joules per grams degrees Celsius. Okay? This is the specific heat of water in joules. And what this means is that if you have 1 gram of water, and you want to raise its temperature 1 degree Celsius, which is about 2 degrees Fahrenheit. So in 1 gram of water, that's a tiny amount of water. That's 1 milliliter of water, which means there are 1,000 grams in 1 liter bottle of water. Okay, it's a very small amount of water. But if you want to raise 1 gram of water 1 degree Celsius, you have to put 4.184 joules of heat into the system in order to do that. Okay, water has an extremely high specific heat. Now, what is it about water that you know where it makes sense that water's specific heat is so high? Think about places people live near really big bodies of water. Like, so if you, let's say you live, I don't know, like right on the beach in Malibu. What's a typical summer day?
100 degrees.
Maybe, right? That would be like a really, really hot
Maybe
summer
like
day.
80.
Yeah, tend to be 80 degrees. What about a typical winter day? 70 degrees? Yeah, I mean, there's not a lot of fluctuation in temperature when you live really near a large body of water. The primary reason for that is water's a heat sink. Okay, it can absorb an enormous amount of heat without heating up very much. Okay, you ever go into the Pacific Ocean in the summertime? Really cold. You ever go to the Pacific Ocean in the wintertime? Not much colder. Well, it's not much
hot.
Yeah, it's not much colder than it is in the summertime. Again, it's because you've got this massive heat sink that can absorb a ton of energy. And so again, yeah, we tend to work these problems using water as our fluid. And so if you wanted to figure out, okay, well, how much heat is a reaction actually requiring? Or how much heat is a reaction actually giving off?
4.184.
4.184. Yep. I did the 8 first, and then I went back and put the 1 in. So yeah, 4.184 joules per grams degrees Celsius. So if we wanted to work out a problem, let's say we had a problem like this. So a reaction in water raises, the temperature 5 degrees Celsius. If there are 750 grams of water, how much heat did the reaction release? Okay, so again, we'll do our typical questions. Want, tools, given. So we're given temperature. Oh, I don't want that. We're given, let's try to get this back into the same spot. There we go. We're given delta T is equal to 5 degrees Celsius. We're given that mass is equal to 750 grams. And tools, we've got Q, or heat transfer, is equal to MC delta T. And what do we want? We want Q, right? We want to know how much heat was actually released. So we'll just plug all these things in. Q is equal to mass, which is 750 grams, times, we also know the specific heat of water because that's a constant, 4.184 joules per grams degrees Celsius, and then times it by our delta T, which is 5 degrees Celsius. Degrees Celsius is going to cancel. Grams is going to cancel. And ultimately we get that Q is equal to something in the neighborhood of, what do we got?
25,104 joules.
25,104
Yep.
joules. So we need to pay attention to significant figures. Our number with the fewest number of significant figures is 1, so we'll represent this as 30,000 joules. And what's kind of crazy is 750 grams of water isn't very much water. You're talking about less than a liter of water. So less than a liter of water, you heated it up 5 degrees Celsius, which isn't very much, and you basically had a reaction releasing 30,000 joules of heat. And it's not raising the temperature of very much water by very much, okay? And it shows you how well water works to buffer against heat increases. It is an incredible solvent, okay? And so this, this equation here, the Q equals MC delta T, this formula gives us a great way to think about and to actually illustrate what's going on when we're talking about a system absorbing heat. And how do we actually quantify that in a way that makes sense? Okay, so we'll do a couple more problems just dealing with this, and then what I want to do is take this concept and link it back with our concept of internal energy, or change in internal energy. Delta U is equal to Q minus W. Okay, and then talk about, okay, if a system does this amount of work and its internal energy changes this amount, how much does the temperature of that system actually change? Because now we can do that, okay? Because we have a way of actually equating Q, or heat transfer, with a change in temperature. Okay? So let's do a couple more problems like this. So let's do this one. If a reaction absorbs 5.43 kilojoules of heat, how much would the temperature of 50 grams of water change? Okay, so this is assuming that the reaction is carried out in water. Okay, so we'll first ask the question, what do we have? And what do we have? We know that Q is equal to 5.43 kilojoules. We know that mass is equal to 50 grams. Joules. We have our formula Q equals MC delta T. Now we'll rearrange this because we're going to solve for delta T. So we'll rearrange this by dividing both sides by MC. Right? And then what do we want? We want delta T. Sorry, I already moved to that without actually plugging this in. So T is equal to Q divided by M times C, which equals 5. Now we'll put this into joules. So kilojoules you multiply by 1,000, right? To go from kilojoules to joules. So this is 5,430 joules. Sorry, that's a 4. Divided by 50 grams times 4.184 joules per grams degrees Celsius. And so then what you end up getting is that delta T, sorry, not Q, delta T is equal to, And so joules will cancel, grams will cancel, and we'll be left just with degrees Celsius, which is nice because that's what we want. And so what do we have for our temperature? 26 degrees Celsius. 2 significant figures. We got to do it in 1 significant figure because I did 50 grams. So we'll do 30. Man. There we go. Let me see if I can replace this. Okay, there we go. 30 degrees Celsius. Okay, since we can only present our answer with 1 significant figure. Sorry about the sloppiness. For some reason my pointer, this is not actually lining up with where it actually draws, which is fun. But at least it's working this week, so we can't complain too much. And so if a reaction absorbs 5.43 kilojoules of heat, you've got basically your water changing by 30 degrees Celsius. Now, is it losing or gaining temperature? So the reaction is gaining because it's absorbing that energy, but the water would be losing that temperature, right? So if your reaction is being carried out in water and this reaction absorbs heat, what you're actually going to feel is that your water is going to decrease 30 degrees Celsius. So now, why did this one change so much compared to our last example? The last example, we had basically 5 degrees Celsius change in temperature, and it was like, 30,000 joules of energy when we rounded to 1 significant figure. We have a very small amount of water here, right? You've only got 50 grams of water, okay? So the less water you have, the less the buffering capacity against heat change. The more water you have, the more buffering capacity you have against heat change. Okay. Does that make sense? Okay, and so, we can do one more equation like this, and then we'll combine our 2 concepts together. All right, and then I want to leave us about a half an hour or so to work on the lab, and I'll have to just record what's going on in the lab when we do that rather than working with the slides. Any questions on this problem?
Oh, is it joules per grams that you wrote on the 4.8.4?
Yes, joules per grams degrees Celsius. Yep.
I couldn't see it, sorry.
Yeah, no. Oh wow, it's off the screen. I'll try to stay away from the edge. All right, a reaction is carried out in some unknown, there we go, solvent. If the solvent gains 40 degrees Celsius when the reaction produces 48,000 joules of heat, and there are 200 grams of solvent. What is the specific heat? So now we have one where we're not dealing with water. So you can't just assume that specific heat is 4.184 joules. We've got to actually do some calculations. And so what do we have? Or what are we given? We're given that delta T is equal to 40 degrees Celsius. We're given that mass is equal to 200 grams. We're given that Q is equal to 48,000 joules. And then tools, we have Q is equal to MC delta T. So if we were going to solve for C, we would divide both sides by M delta T. And we want C. So C is equal, we want C. So C is equal to Q divided by M delta T, which is going to be 48,000 joules divided by 200 grams times 40 degrees Celsius. What do we get C is equal to? 6 joules per grams degrees Celsius. Now I told you before that water, as far as I know, has the highest specific heat of any substance on Earth. And so what we would be dealing with is a solvent that is, completely unknown, because that would be a higher specific heat than what you get from water. So now we've done problems where we've calculated for everything except the mass. But if you're calculating, or if you're trying to calculate the mass, it would be done like anything else. You just have to manipulate this problem, or this formula, Q equals MC delta T, and solve for mass. Okay, fairly straightforward. And that's the nice thing about thermodynamics, is all of your calculations tend to be very straightforward. But now we have a way of actually, I think, providing some nice meaning to what we say when a system is absorbing heat, or if a system is releasing heat. We have a way to actually equate that to temperature, which is something more easily understood, I think. So then what we can do then is combine our two formulas from last week and this week and say that delta U is equal to MC delta T minus work. You see where I got that? Since delta U is equal to
Delta U or MC delta T
is equal to Q. Yep. So since Q equals MC delta T, we can now plug in that to our formula for a change in internal energy. Yeah, and so if if you've got a problem where it asks you, how much work can be done by a system if the system absorbs, or the system increases 5 degrees Celsius while its internal energy changes a certain amount, there's a way you can do it. You just combine our two equations.
Can we do one of those?
Yeah, absolutely. Absolutely. Not only can we, I think we should. So let's say this. Yeah, let's just use that. So how much work is done when 100 grams of water increases 40 degrees Celsius while its internal energy decreases by 50 joules. Let's do 50 Yeah, we'll just leave it as 50 and work with one significant figure. Although we'll get the value initially and then we'll round it to one significant figure. So how much work is done when 100 grams of water increases 40 degrees Celsius while its internal energy decreases by 50 joules? So let me give us a new slide. And what do we have? So we have that delta U is equal to 50 joules,
50 joules.
right? It increases 50 joules,
Yeah. Or decreases by
decreases, so negative 50 joules. We know that the mass of water is equal to 100 grams. We know that C is equal to 4.184 joules per grams degree Celsius because it's water. And we know that delta T is equal to, what do we have for our change in temperature?
40 degrees Celsius.
40 degrees Celsius. So tools, we have delta U is equal to MC delta T minus work. And then what do we want? We want work, which equals, doing a little algebraic trick, MC delta T minus delta U. So work equals mass, which is 100 grams, times 4.184 joules per grams degrees Celsius, times 40 degrees Celsius, minus, so then it's going to be minus a negative, so actually be plus. No, stop. 50 joules. Okay.
Is that negative or?
It's plus because it's minus a negative. Since delta U decreased and we minus delta U away, when we minus a negative, it ends up becoming plus.
The one before it, is that 10 or 40?
40. Sorry. It crowded. So grams is going to cancel, degrees Celsius is going to cancel. For the first part, we'll be left just with joules. Second part, we'll be left just with joules. We'll be able to add them. The nice thing is, when we add, we can maintain the same number of decimal places, which is 0. So we don't actually have to limit our answer to one significant figure.
Mm-hmm.
So what's our answer?
I got 16,786. What did you get?
16,786.
Mm-hmm.
So 16,786 joules. And so that's how much work can actually be done. If your system is water, it gains 40 degrees Celsius, while its internal energy decreases by 50 joules.
Would you have to change it into 16,000 or 60?
You wouldn't have to in this case unless you did your significant figures initially and then added. But if you wait till the end to do your approximations. So I would say that in this one, if you presented this answer, I wouldn't mark you down at all since you have both a multiplication with significant figures and a subtraction going on. If you wanted to, that would be fine. If you wanted to then round it to 20,000 joules, that would also be okay. Actually, what you would need to do is over here, you would have had 16,736, right? Over on this side. So 16,736, if you rounded that to one significant figure, you would have 20,000. And then when you add 50, you would have 20,050. So either way you presented it, I think would be fine. You would either need to present it as 20,050 joules or as 16,786. So that's where it gets a little weird. When I actually give you problems, I'd make sure to give you 50.0 joules, 100.0 grams, so you'd have enough significant figures to not have to do that amount of rounding. because the difference between presenting your answer as 16,786 joules and 20,050 joules, it's a big difference. It's a really big difference. All right? Any questions? You feel fairly comfortable working through these? Again, that's the nice thing about thermodynamics. The calculations are not super complex. In fact, they tend to be very straightforward. It's just the actual concepts tend to be a little bit more complex than when you're dealing with kinematics. So you kind of have both issues in physics. Either your calculations are easy and your concepts are a little weird, or your concepts are easy but your calculations are a little complex. So, all right. Yep, we'll keep those. We'll stop this.